decade touring the world, implementing lighting and sound solutions for stage applications before he became the specialist for Nextlight. His electronics background and love for gardening eventually led him to the world of cutting-edge horticultural lighting, where he's consulted clients ranging from hobbyists to large-scale commercial installations all the way throughout. Nextlight, like I was telling a little bit before, I don't know if you guys were in here, I've been using the Nextlight Veg 8 for a while now. I put it up against my T5s, blows them away. It's full spectrum, crazy, crazy good. You'll save money not only on the power, but the heating costs from that. It's great all the way around. But without any further ado, we're going to get my boy up here from Nextlight, Alex. Give him a round of applause, everyone.
Thanks, everybody. Special thanks to Grow Green for putting this on. This is our second year here, and this is definitely much bigger than last year. So glad to be here with Grow Green. Everybody give them a round of applause. It's good to see that a brick-and-mortar retail business can still make it in 2017. I think our industry is kind of a testament to that. We stand a little bit apart. But enough about that. Tell you a little bit about Nextlight. We have been selling LED grow lights since 2013. This was our original light. We call it the 525 now. It was originally just called the Nextlight. What we did with that, we basically did pretty much what everybody else was doing with LED lights. We took a bunch of high-power diodes, squeezed them into a small package. We actually were using 10-watt Cree diodes made in the United States. So we wanted to use the highest quality we could. We used Meanwell drivers. We put the whole thing on heat sinks, added some fans. Ended up being a nice heavy-duty, heavy package. The main difference between what everybody else was doing and what we did with that is we used all white light. Where most other manufacturers were doing the purples, where they're using red and blue diodes to get a purple overall look. We just went straight for white light. Not really very many other people were doing that. So our engineer just kind of wanted to see how plants would grow under a more natural type of light instead of using the targeted spectrum that everyone else uses. So we sold that light for a couple of years, got some feedback on it. Main feedback being it was too intense and too small of an area. The reason being that light was originally designed for greenhouse usage. Our CEO engineer, his dream was to have a food production greenhouse. But it turned out after playing with that light for a couple of years, the guys in that industry aren't really quite ready for the most part. They're used to getting free lighting from the sun, so the thought of paying a bunch of money for LEDs, even with the promise of longer life and higher efficiency and all that, it just wasn't really the right market. So after a couple of years of selling that type of light, we moved on to what we sell now, which is the commercial series. First light in the commercial series is the Nextlight Mega. The main difference with all these lights and what you'll see in most of the market and what we were doing before is no more fans, no more heat sinks. Instead of high-power diodes, we're now using a Samsung middle-power diode. And instead of using 98 diodes that we were using before, the Mega has over 2,500 diodes. So you spread out the footprint of the light a lot more. You lose the fans and heat sinks because you don't need them anymore. Everything's cooled passively. It's a lot simpler build, a lot more efficient. So the Mega is our main commercial light. It'll do a 5x5 footprint in flowering, up to a 7x7 footprint in veg. 650 watt actual power draw. The total photon flux, or PPF, of the unit is 1400. So that puts us just a little bit lower than a dual-ended 1,000 watt dual-ended high pressure sodium. True output of that is going to be about 1,700 ppf, but we direct a little more of that light towards the canopy because diodes, LED diodes, are so directional. So we consider this our dual-ended 1,000 watt replacement. Even though the total light output is just a little bit less, it's fuller spectrum, and we direct more of that light at your canopy. Again, 650 watt actual power draw, so that gives you 5.4 amps at 120 volts, 2.7 amps at 240 volts. The Veg 8 is our main veg fixture. Even though you can veg with all of them, we do the same spectrum. The Veg 8 is designed to replace an 8-tube T5. Typically, an 8-tube T5 is going to use about 430 watts. Our Veg 8 uses less than 190 watts, actually. It is the same size fixture, covers the same size footprint, a little bit more light output, and, of course, a lot fuller spectrum. And then we have the nextlight Mini. This is our hobbyist light. This is your replacement for 400-watt HPS. This is for your small hobbyist guys in closets, people with really limited space, low ceiling height, can't deal with a lot of heat. This is kind of our answer for them. So everything we do currently is 100,000 hour life rating. Most other LEDs you see out there are going to be about 50,000 hours. This is based on L70, which means at the end of 100,000 hours, the light is going to be at 70% of its initial brightness. So 100,000 hours in terms of a 12-12 flowering cycle, that's about 22 years. So to put it in a little more realistic terms, after about 7 years, you're still going to be at 90%. So realistically, in 7 years, you're probably going to be moved on to something else. We're going to have a lot more efficient technology for you. Things are going to change, but at that point, you'll still be at 90% of the original life. We warranty it for 5 years, and that is a full warranty. And anytime during that 5 years, if you have a single diode go out, we'll actually overnight you a new fixture. Everything we do is also will run anywhere. It says 120. It's actually 100 volts to 277. That's on all our fixtures standard. There's no switches. You just plug it in, and it recognizes the voltage. And then on the commercial level, we can do custom options for three-phase, the higher voltages, your 480, and so on. Everything we do is also UL certified, and we're actually IFAU certified, which is UL's horticulture-specific certification. We're one of only a small handful of LED grow lights that has that. Of course, no bulb replacements because it's LED, and everything we do is made in the USA. We actually manufacture in Spokane, Washington. So I want to talk a few things about what sets us apart and what you'll notice about us compared with other lights out there, especially other LEDs. First thing you'll probably notice is spectrum. Like I said before, we don't do the targeted spectrum monodiodes that most of the other manufacturers are doing, the blues and reds with a few other colors speckled in. The diode we use is considered a phosphor coat white diode. So what it actually is a very high efficiency blue diode. You can see the big blue spike there. And they put a phosphor coating over it. And that phosphor converts the blue into the broadband spectrum that you see. So you lose a tiny bit of efficiency with the phosphor coat, but you gain the spectrum. That is what most of the diodes you see in the world are. You know, restaurants, airplanes, highways, any of the white light LEDs you see out there are going to be using this technology, and consequently, the manufacturers of these diodes, Cree, Osram, Samsung, they put their most work and their most R&D into these type of diodes because they have the most money to make off of these type of diodes. So that's one more reason that we chose to go with the white light spectrum, is because the quality of the diodes was so much better. Now, who here has ever heard that plants don't use green light? Couple of people. All right. Well, not too bad. There is some basis for that. It's not total garbage. There's a set of proteins in the plant that respond to mostly far red light, and that tells the plant to wake up and go to sleep. Those proteins are not sensitive to green light, so that's why you can take a green light in your garden with the lights out, and it won't affect their cycle too much. But plants absolutely do use green light for photosynthesis, and there are a couple studies I'll talk about later on. So one of the main studies that people cite a lot when they're talking about the types of colors that of light that plants use is the McCree studies, or the McCree curve. So Dr. Keith McCree, he was a professor from Texas A&M. He did a series of studies in the late 60s, early 70s to try to determine what colors of light plants use. So he did a bunch of different types of food crops. He grew them in chambers, outdoors, did a bunch of experiments, to try to figure that out. And what he measured was the amount of CO2 that the plant fixes with each type of light. So that was the metric he used to determine how the plants were using it. There were a few, it's a really good start. It gave us a lot of information about what kind of lights plants use. There were a few limitations to his studies. He wasn't really doing whole plants. He was doing leaf segments. He was also doing them under really low light conditions. So most of us, especially in this industry, we're not growing leaf segments or single leaves, and we're definitely not growing under low light. Most of us are growing under high light conditions. So this is the McCree curve that he came up with that is what most people still use to determine how efficient their spectrum is. Although, as you can see, there definitely is a lot of green in there. Even though it is the lowest point, it's not really much lower. It's about 17% dip there. And we'll get into why that is a little bit more. So this is what most LED manufacturers do. They're trying to target the high points of the McCree curve using the blue and the red. Again, there is some science to that, but as you can see, there's a lot in the middle that is missing. This is your classic 1,000-watt high-pressure sodium. I believe that's Hortilux. So high-pressure sodium is the opposite of what you'll see with most of the purple LEDs. It's a big spike of yellow and green in the middle, fairly decent amount of red, very little blue. So if plants really didn't use the yellow and green, high-pressure sodium would be a pretty poor spectrum, but as we've seen, it's the industry standard. It obviously works. Could you go back one? So this is our spectrum. Like I said, it's the same spectrum we use on all our lights. We use a combination of 3,000 and 5,000 Kelvin. They're both white light diodes. The combination gives us a 4,000 Kelvin correlated color temperature. And as you can see, if you're going to go with the McCree curve, we match it pretty closely. So here's one of the studies talking about green light. This was published by University of Tokyo in 2009. The title is Green Light Drives Leaf Photosynthesis More Efficiently Than Red Light in Strong White Light, Revisiting the Enigmatic Question of Why Leaves Are Green. So I won't go through too much of this. You can look it up on your own. Go to the next. The basic idea of this study is that, yes, plants do absorb plants absorb red and blue light very efficiently, actually so efficiently that most of the red and blue light get absorbed in the top layer of the leaf. The green light doesn't get absorbed quite as efficiently, so it penetrates a little bit deeper into the leaf. And actually, a lot of the light goes all the way through the leaf, going down further into the canopy and bouncing around. So it does get used, it just doesn't get used in the top layer of the canopy quite as efficiently. Not sure what that one is. I think I was missing something there on the last one. But the idea is that the green light, even though it's not absorbed that efficiently in the first place, it does penetrate deeper into your canopy. It bounces around within the leaf, within the canopy, so it does get used. And that's one reason high-pressure sodium penetrates so well, and one reason most LEDs don't have a reputation for penetrating very well. Blue and red light gets absorbed really efficiently, but there's not much left to penetrate down into the canopy. This is another study done about green light and just spectrum in general. Bunch of different plants grown under a bunch of different spectrums, from monochromatic red, monochromatic green, warm white, red and blue, red, green, and blue, all under equal lighting levels, so just to isolate the spectrum here. And what they found out was under low light conditions, there's almost no difference. And under high light conditions, there's not that much of a difference. You'll start to see in the monochromatic red, monochromatic green, monochromatic blue even, there's some issues there. But generally between the all-white LEDs and the red-blue, red-green, blue, there wasn't an increase with just the spectrum alone. If you're keeping equal light levels and you've at least got a somewhat full spectrum, from what this study shows anyway, the growth levels are pretty equal. So next thing you'll probably notice is the size of our fixtures. Our fixtures are very large. We wouldn't do that if we didn't have to. Most of the fixtures that you see are going to be around 20 inches by 25 inches. They might have 100 or 200 diodes. The Mega, as I said before, over 2,500 diodes, and it's quite large. It's 35 inches by 35 inches. That being said, it is very lightweight. No heat sinks, no fans, no LED screens or remote controls or anything. We keep it really simple. We don't want this to be the as seen on TV hammer. We want this to be your grandpa's hammer. So we keep it lightweight. We keep it really simple. We don't even paint the thing. And one of the main reasons we do that is for footprint. So if we're going to talk about footprint, let's talk about what the pros do. Dual-ended high-pressure sodium gives a very wide throw. And a lot of LED manufacturers will claim this is a weakness because, yeah, you are losing some light on the walls. It's not all being directed down at your plants, but it's actually in a commercial setting, this is a lot better. You use multiple fixtures, you get overlap, you end up with really great penetration, really even uniformity everywhere, so that's what we wanted to strive for. With the normal LED, LEDs are directional just by their nature, so they're going to want to shine in one direction. A lot of manufacturers will put lenses on there to try to either spread the light out or in some weird situations even focus it even more. Not really sure why you'd want to do that with a diode that's already very directional. So what they do is they add a whole bunch of diodes, but they're still all very directional, so you end up with a hot spot. No matter how you do it, how you add lenses or whatever you try to do, the brightest point is going to be directly under the center of that fixture. So what we did instead is we made a really big fixture with a blank spot in the middle. So we spread our diodes out, and we don't put any lenses on there. We just give it its natural 120-degree beam angle, and it functions a lot more like the dual-ended high-pressure sodium. But, of course, since it is LED, it is still somewhat directional, and you're not getting that light shining straight out to the sides. So that was kind of our compromise in between. Now, one reason that a lot of LED manufacturers do this is because it looks really good on a par meter. That's a Lycor par meter. That's going to measure PPFD, photosynthetic photon flux density. Basically, that's the amount of plant-usable light at a single point. So if you have all your diodes aiming at a single point, it's going to look really good on a meter. The problem with that is this is my iPhone on the same Lycor meter, and with the iPhone flashlight, I can get a reading of over 8,000, which would cook any plant known to man. So the single point PPFD numbers, while it can be useful to go into your garden to use a meter and kind of know the light levels you're getting, it definitely doesn't paint the whole picture of the light. It's just telling you how bright that light is at a single point. So going a little bit further than that, you can do par mapping, which we do. This is one of our par maps for the Mega. You take one of those same par meters. This is an apogee meter in this case, and you do a bunch of those single point measurements, and you map it over a large area, and that gives you a little bit bigger picture of what the light's actually putting out. Instead of just seeing how bright it is in the center, you can see how bright it is over your entire area. And some people will try to take that map and do some math and kind of reverse engineer the efficiency of their light. That's not real scientific either, so we kind of have to take it a step further. This is a machine called a goniometer. There's a lot of different types of them. What this does is it kind of takes those variables out of the equation. It takes your reflector, your LED, kind of swivels it around. Instead of taking a bunch of single points, it's measuring the intensity from every possible angle. So with that, we can generate IES files that give us a lot of information about our lights, and we can actually put it in lighting software and calculate not just single points, but we can actually do entire room layout mapping. We can see where the bright points are, not just on the plant canopy, but on the walls, at different layers of the canopy. So for our commercial clients, we do plots like these so they can get a really full image of what their garden's going to look like. This is another type of plot that we'll do. We can actually put some of the room elements in so you get all the reflections, all the shadowing and everything. A lot more accurate than just a simple single point. This is a device called an integrating sphere. This is the device you want to use if you really want to see how efficient your light is. You put the entire light in the sphere, it captures every photon coming off, and through a bunch of math, you can determine how efficient your light is. So that's what true manufacturers use. A lot of companies either don't have access to one of these or just don't really care, and so they either don't publish their numbers or they publish some false numbers. So this is just a little chart. Try to rush through this a little bit. Just kind of comparing some efficiencies of different lighting technologies just to give you an idea. And this is based on that integrating sphere calculation where it measures all the light coming out. So lumens, we all know lumens are for humans. That's what we base human eyesight on. So it's not the best thing for measuring plants, but it is what we used for a long time. It's great for office buildings and warehouses, that kind of thing, where we need to see. So I still put it on here because you need to see in your garden. So it is a factor. Fluorescent, what you typically see in office buildings, warehouses, that kind of thing, 60 to 90 lumens per watt. So they're putting out 60 to 90 lumens of light per watt of electricity that the light uses. HID, it's a little better than that, 120 to 130 lumens per watt. Some of the really poorly designed LEDs, stuff that you'll see on Amazon, now obviously it's not made for human lighting, so it makes sense that it wouldn't have a high lumen per watt, but you'll see really low, 25 to 45 lumens per watt on that. Well-designed white light LED, we're seeing over 145 lumens per watt, which is why you see white light LED making its way into every commercial lighting application in the world because it is more efficient. Another way, probably the most common way right now that people measure efficiency is with micromoles. This is a PAR measurement, so it's measuring plant usable light. Fluorescence, pretty poor, usually between 0.9 and 1.1 micromoles per joule. That's also what a pretty poorly designed single-ended high-pressure sodium would give you. With dual-ended high-pressure sodium and ceramic metal halides, some of the different more efficient HID technologies, we're getting a little more efficient in the 1.4 to 1.8 range. Some poorly designed LEDs, most of them will not actually advertise their efficiency because they're basing their sales pitch just on their spectrum. They don't want you to know how much light the unit actually puts out because it's usually pretty low. So again, we're in that 1.1, 1.6 range. And some of the best designed LEDs out there right now are over 2 micromoles per joule, which, by the way, micromoles per joule, it's the same thing as ppf per watt. If you see that, this is just the more nerdy way of saying it. But all the best high-end LEDs out there now you'll see are greater than 2 micromoles per joule. I've seen as high as 2.7. Eventually, we're going to see that above 3 mark be hit. The last way that we measure light is radiant flux or radiant efficacy. That's measuring the actual light output in wattage. So each photon that the light puts out carries a different energy level. The shorter the wavelength, the greater the energy. So blue light has more energy than red light. Energy that is turned into light is counted as radiant flux energy. The rest is turned to heat. Fluorescent are really inefficient. They're turning less than 15% of the input watts into light. HID, the best HID is around 34% efficiency, and the rest goes to heat. There's some poorly designed LEDs that we've seen out there with under 20%. I've seen as low as 11%. And well-designed LEDs are greater than 45%. So if you notice here, every grow light out there is actually creating more heat than it's creating light. So we're working towards that point. LEDs are slowly getting more and more efficient, so eventually we'll see that above 50% mark, but it's something to keep in mind is that every grow light out there is actually producing, no matter what they say, zero heat, every light out there is producing more heat per watt than it produces light per watt, unfortunately. So just a quick cost breakdown. Am I doing all right on time? All right, real quick. So this is based on 10 high-pressure sodium lights, 10,000 watt high-pressure sodium. Startup costs on that is going to be about $6,500 retail price, 36,000 BTU AC. Now, keep in mind, this is just to cool the lights. This is not counting the AC that you would need just to cool the room without the lights in it. So just basing this on that. So that's going to be about $10,000. Your friends at Grow Green are going to give you a nice discount. So we'll figure about $8,000 for that initial startup cost. LED is going to be a lot higher startup costs. About $17,000 retail price for 10 of our nextlight megas. Going to need a slightly smaller AC because we are about half the overall heat output. So we'll go with the 24,000 BTU AC for $3,000. After your discount, you're still going to end up about $16,000. So about double the startup costs of high pressure sodium. So we start looking at our year-to-year costs. Measure that in kilowatt hours. So high pressure sodium lights with just the lighting is going to be a little over 43,000 kilowatt hours the first year. Air conditioning is going to be a little over 14,000 kilowatt hours based on the national average of about 13 cents per kilowatt hour. You're paying $75.92 in energy costs that first year, plus your maintenance costs, your bulb changes and your reflector changes that all these manufacturers recommend you do once a year. It's going to be about an extra $2,000. So you're looking at about $9,500 your first year with those 10 high pressure sodiums. We still got the 28,000 kilowatt hours of lighting energy, 9,000 kilowatt hours of AC energy, but no bulb costs, no reflector changes. So quite a bit less, about half the total cost that first year, $48.53. So year over year, you add the startup costs plus year one energy costs, year one maintenance costs, year two energy costs, year two maintenance costs. Those lights are going to cost you to buy and run for 2 years, a little over $27,000. Our lights, startup costs, energy costs over 2 years, it's going to be a little less than that, about $25,000. And then we still have, like I said before, you've got 7 years on our lights until they're at 90% of their initial brightness. So consider you're going to use them for 7 years. That next 5 years is just going to be savings right in your pocket. A little under $5,000 per year of savings based on 10 lights. Last thing here, we are DLC premium listed. DLC is a company called Design Lights Consortium. You think of them as Energy Star, except for lighting. They're a certifier to determine if your lights are efficient and have long life. Essentially, this is for the power companies who do rebates. This lets your power company know, hey, this light has our stamp of approval. It's efficient. It's got a long life. It's going to save you money. So we'll give you the rebate. Now, I don't know if the rebates are really here in Michigan yet. We have a rebate guy on our team that knows all that stuff a lot better than I do. But in California, Washington, people are saving over $300 per fixture from their power company when they switch from high pressure sodium to our lights. Thanks.